Okay, the last video was the introduction, and now we are discussing, or this is the first lecture in junction with our introduction. So here in this lecture, we will, or I will, formally define three versions of what we call a relationship in the context of mathematics, of course. Well, it's a bit laggy. My phone's a bit laggy. Okay. So what is a relationship? Let's ask ourselves the big old question. What is a relationship? Now, you guys know in real life, a relationship is a relation between two peoples. Whether it be a girlfriend, a boyfriend, a civilian union, a marriage, whether your relationship with the person is that they are a relative, a blood relative, your mother, your father, your brother, your sister, your son, your daughter. This is a relationship. Or a relationship, we can say, is a measure between what, or the degree to which what one is related to another person. That is a relationship. But in the context of relationship theory, we will throw that definition out the window and abstract it using the language of mathematics. So there are three versions of what we call a relationship here in relationship theory. The first form is that it is a graph. One, it is a graph, which I will expound upon in this video, or at least in this lecture. So we have three types. We have three types. So first it is a graph, G, or I'll call it R, not a ring, which is an ordered pair, R bar, and E. So it is a graph, or the second one, it is a system. Governed by the three-bodic problem. And the last one, it is a topological relationship, or a topological structure. And this is where we apply our lecture with regards to topological relationships back in femboy theory. Especially we're going to talk about REL, of course. And in fact, this is how I'm going to prove that maybe there are graphs that may be manifolds. Okay? Okay, so in this lecture, we're going to discuss the first type. The first type of relationship, which is a graph. Now, let's ask ourselves the question, what is a graph exactly? A graph is a mathematical structure. It could probably be a geometric structure as well. The thing is, in graph theory, we don't really care about the notion of the length of it, but in this theory we will care about the length of what a graph is, or of a graph, or the edges of the graph. Now, graph theory has a lot of applications in society. Well, the first thing is that it is used in social sciences to draw correlations between various variables concerning the behavior of individuals in society. It's also used in chemistry to model the structure of crystals and other chemical structures, of course, and also especially data sciences or software engineering. It's also used there. So let's formally define a graph. What is a graph? So this is our first definition. Definition 1. A graph is a mathematical structure which I will call G, which is the ordered pair. Here in this case, we're gonna be using the angle bracket notation for ordered pairs, so that we can differentiate between what an open interval is and an ordered pair. But most mathematicians actually just use the ordered pair like this, using the parentheses. But we're using angle brackets here. Same thing anyway, doesn't matter. G with a set of points or vertices and a set of edges with G bar, a set of vertices or points, and E, a set of edges. Okay, so this is our first definition. Now the thing is, you guys need to know a little bit of the jargon used in graph theory. Excuse me. Okay, so a more formal way of defining E is that E is a subset.
Hello, morning.
Oh, morning, sir.
Lalagay lang ako dito.
Okay, sir.
Oh, meron pala dito ba? Updated. Hello. Sige, kain na tayo. No problem.
Okay, so E is a subset, but not entirely the set of, or is part of actually, all unordered pairs x, y, such that, well, x and y are inside or are part of G bar, and that x and y are not equal. So what we're saying is that this set here is the set of all possible connections we can make between the points x and y inside our set of points G. So once we equip this G with this subset of this set, we have ourselves a graph. And a way of visualizing this is like this. So we have a point. It could be solid or hollow, it doesn't matter. And then another point here. Call it y. And this is an undirected graph. Or, yeah, an undirected simple graph. Now the thing is, simple graphs are only simple graphs when they don't have loops in them. And a loop is when we have an edge that goes from a point to a point. Now this over here is not a simple graph, but a pseudo graph.
Bye, guys.
Alright, sir. This here is not a simple, the one with the loop is not a simple graph, but is rather a pseudo graph. A loop permitting multigraph or pseudo graph. So E now, the set of our edges is part of all possible edges we can have. But why not just say that it is just all of these? Why not just say that E is just a stand-in for this set? Well, we can't. That's why we put this equals to sign here. So E can be either just a subset or it can be the entire thing. Which is why we put this equal here. That's why I didn't just write this. Alright, that's why I didn't write but not equal to. That's why I didn't write that. That's why I write this. Because it can be this. In fact, in most cases, E is that. Okay. Okay. So, now how do we denote graphs that are directed? So, right, we have an undirected graph between 2 points, x, y. And then I'll call this line x, y with non-LaTeX letters. Okay, x, y here. So it's two connected. It shows that it goes from x to y. Now this would be the same as yx, which is going from here to here. So xy is pretend that we're traveling along the line from x onto y. And then it's the same as going the other way. Okay? That's an undirected graph. Okay? So now, what if I have a graph, well, AB. But this time, I'm going to say it's not equal to BA. This is a directed graph. And most people show this or use this kind of thing here. Or we can use an arrow that goes from here onto here. Either way, it doesn't matter. As long as we show where the line is going, that is a directed graph now. And we're showing that when we put these strings together, when we make a word out of these two to show where we're going, it doesn't really commute. Okay. So this is a directed graph, this is an undirected graph. Now, the edge A here, or X here, is incident to B and Y respectively if X and Y exists. So I'm saying that this point here is incident to this point, and this point is incident to this point if this edge and this edge exists. If there's something connecting it. Okay, so that's one of the terminology. Next terminology. Okay, so what if I now remove X? What if I now remove X and this vertex XY? Okay, keep in mind this AB and BA. Or this is just AB. And now I connect A and Y. Now we say that the vertex A is adjacent to Y and B because there is an edge connecting A to Y and A to B. We have AY and AB. So we're saying now that A is adjacent to Y and B. I know it's a notion meant for edges or for the lengths of a triangle, but this is just terminology used here. We need to get familiar with it. Okay, so I guess what I'm doing now is just a refresher before we actually go into the meat of today's lecture. Okay, what if I now, okay, so let's grab X from a while ago, which I erased or removed.
Hello!
You keep interrupting, it's not funny anymore.
I tried to stop him.
Yeah, it's legit not funny anymore.
Hey,
He's
bye.
doing it on his own.
Okay, bye-bye.
I said no.
I'll go to you guys later when
You
I'm
do?
done. Okay, I'll hang out with you guys later. Okay. So what if I grab the point which I removed a while ago, which is X, and then bring it out here, so nobody goes to it. That is an isolated point. So now X is an isolated point because no edges are connected to it. Okay, so that's pretty straightforward. Okay, so now let's talk about walks. Okay, so I have this graph, y, a, b, and x. Let's say I want to connect y to x again. Let's make it not lonely for the time being. Okay, and let's disregard the denotations for these guys again. And this time, let's make the connection between A and B an undirected thing. So the subgraph AB is undirected now. So AB is equal to BA. So I have the graph BAYX. Okay. A BX walk, or B to X walk, is a sequence of strings here that sends the point B to X. So let's say we're standing at B right now. A walk is basically us traveling in sequence between these vertices to a terminal or final destination or point. So the BX walk here would be BA, or rather BA, AY, BA, AY, YX. That is a walk. So I'm going to use these dashes here so that you guys can differentiate them. That's a BX walk. So it is a sequence of, oh well, I have to put B here. The point B, or the vertex B, and then the vertex X. So I'm going to use hat to denote these guys. Or I'm going to use dot. Or no, I won't use them. Just the points themselves. So I'm going to put parentheses here so you guys can differentiate them. Don't get confused. So now, this sends B to BA first. Alright, so we read from left to right like we would when we're trying to do normal elementary algebra or elementary pandas or operations. And we first travel along the vertex BA onto A. Once we reach A, we travel along the vertex AY to get onto Y, and then travel the final vertex YX to get us to X. So that's a BX walk. Now, okay. What if now I close this graph, or make it a closed convex shape? What if I make it convex now, and connect X and B? So I create the vertex XB equals BX, undirected subgraph now. Then, we now call this entire graph a closed graph, because there is a walk that leads from B onto itself that isn't a loop. So now, a BX closed walk is the case wherein X is equal to B. So that means we travel along the entire graph only to return to B. Now that's a closed walk. Okay, so now we know this walk here, right? It goes onto X here. Okay, so the thing is, when we do walks here, we can repeat edges normally. So I can travel along B and X. So I can do this walk here. BX, and then XB, and then BA, and then AY, onto the point Y. So, okay, this is a BY walk, but the thing is, what I did here was walk along here, going here, and then return. What we did was repeat an edge. But what if I don't permit that kind of movement here in the graph? What if I don't permit that kind of walk? Well, then now, we say that any walk that doesn't do this, that doesn't repeat an edge, is called a trivial walk. So I'll walk like what I said a while ago. BA, B first, and then BA, AY, YX, and then XB is a trivial walk. But what I just stated just now is not a trivial walk, because we repeat an edge. We travel along this edge again after traveling along BX. We travel along XB now, so we just repeat the edge. So it's not trivial. Okay. That's a trivial walk. Oh, sorry. I need to repeat myself. That what I just said was actually called a trail. That's a trail. Sorry. What I just said was a trail. Now, a trivial walk is just a walk. That's just the point. It's not a loop. It's not a loop, but just, you know, if I have the walk A, just A, that's a trivial walk. That means we don't do anything. Okay, this is a trivial walk. A trail is what I said a while ago, where we don't repeat the edges. Sorry for that discrepancy, but yeah. A path now is a walk with no repeated vertices. Okay. So trails can not repeat vertices, not repeat edges, but it can repeat vertices. So I can go along A here, and then Y, X, B, and then back to A here. I can permit that, but if I don't permit that, and traveling along the edges, we have ourselves a path. Okay, and I think this is our last terminology. And then two more terminologies. So a cycle is a closed path. So now we're allowed to permit the traveling onto B here. So we travel from B to A to Y, Y to X, and then back to from X to B. We permit the first vertex. It's called a circuit. And last terminology. Okay, so this graph is connected if there is a connection between all of these vertices. So if I just move this Y up here and connect Y and B, this is now a connected graph. Because for every vertex here, or every two vertexes here, there is always a connection. So Y and B have a direct connection. B and X have a direct connection. X and Y have a direct connection. AB has a direct connection. AY has a direct connection, and then just draw one more. And now AX has a connection. A and X has a connection. So now this graph is connected. It's connected graph. You notice it kind of looks like a icosahedron or a tetrahedron. Now you have the base, and then we have the two faces. Yeah, it's pretty neat about it. Okay. So now if I try to isolate these subgraphs, so okay, I break off A and B, and then YX here. Okay, now I have two separate graphs, BX and AY. Now we have two subgraphs. So what we can consider these guys as like two separate graphs, but what we want to do is consider them as one whole graph, and just say that these guys are components of the graph. So then we say, if this is our graph G, we say that the kappa of G, or our components of G, is 3. So the kappa of G, kappa, maps G onto R. Precisely, it gives us, or it's a function of G, or the components of G, and tells us or asks us, what are the amounts of subgraphs inside our graphs? What are the amount of components that we have in our graphs? Or actually here, this is 2 actually, not 3. So this is 2. Since we have 2 subgraphs, we have 2 components. The kappa of G, or the bound components of G is that. 2 components, precisely. Okay, so now, the amount of vertices of this graph is called the order of the graphs. So the order of G here is 4, because we have 4 vertices. And now the degree of the graph is the amount of vertices it has. So the degree of this is 2. So you have 2 vertices. If I connect A, B, and Y, X again, the degree changes from 2 to 4. And if I add another point here, which I will call rho, and connect it to X, our order now changes from 4 to 5, and thus, since I connected rho to X, I now have a degree of 5. Or if I remove rho, if I remove the vertex rho, and connect Y and B again, we have a degree of 5 also, even though we don't have a separate vertex or a new vertex. Okay. So now, given this information, let's now classify 2 specific types of graphs. We have a simple graph, and then we have the pseudograph, or or the multigraph? The simple graph is basically just a graph that has two vertices and one connection between them, whether undirected or directed. A pseudograph now, or multigraph, is a graph that has multiple vertices and thus multiple connections between them. They ask me, how about a graph that has two isolated pairs of points with like this? Well, we still consider a multigraph because we're considering the whole. If we're just considering these guys as individual graphs, they are just simple graphs. Now the thing is, when I do this, if I make a loop, or if I make an edge that goes from one vertex to itself, this becomes a pseudograph because simple graphs only or do not permit loops in them. So given this information, let's now formally define the first type of what a relationship is. Okay. So this is a very abstract definition, but a relationship is a graph, which I will call R. It's the ordered pair P and E. Okay. So this is definition 2. With the set of all vertices which act as abstractions for people and E, the set of all edges that abstract relationships or relations among the elements of P. Okay, so that is a relationship in the context of our, in the context of graph theory. So now we think of the set of vertices over here, let's say this simple vertex here, as a relationship between two people. Now it is up to the reader or the instructor to specify what exactly the relationship is, whether it is a maternal, paternal, a familial relationship, whether it's a platonic relationship, whether it's a romantic relationship. You need to specify what exactly it is in, I guess, your context. But we mean this in the general sense of the person knows the other person, right? And so we can say, oh well, since these guys are persons, right? We can say that, well, what if we say that they are actually persons from person theory? Or these guys are, we can say that maybe they might be position states that are part of our O cross D interval or O cross D space. Well, yes, we can do that. We can definitely do that, but I guess that's for another time. Or maybe I will do that to prove. I'll use that to prove that some of these graphs can be manifolds. Okay. So what do we do with this definition? Well, let's explore. And let's discuss about, well, what about the different types of relationships we have? How do we denote those guys? Okay. So in society, we have two main types of romantic relationships. So in the general sense here, we're referring to the romantic side of relationships. So your girlfriends, boyfriends, or something like that. So there are two main types, right? There is the monogamous relationship, and there is the polyamorous relationship. Monogamous and polyamorous. Monogamous is basically just two people in the relationship. Polyamorous is multiple people in the relationship, more than two. Like how mono here can be an allusion to a monomial, which is a mathematical expression that only contains one member inside it, one thing such as, well, just x. And polyamorous is an allusion, or this poly here, is an allusion to a polynomial, multiple stuff like x squared plus 2x plus 4. This is a polynomial. This is a monomial. So mono means just, well, one pair, and poly means multiple pairs. All interconnected, obviously. Now, what is a monogamous relationship in our context here? Now, a monogamous relationship, so consider our third definition, a monogamous relationship which we denote 2p mono of p1, p2 is a directed graph or undirected graph depending on which relationship you have. We're going to discuss these types later. Consisting of the set p1, p2, and one relationship R or one edge R. Later check. So we have one person here, another person here, and we just connect them. We have ourselves a monogamous relationship. So this edge is the R, this is P1, and this is P2. What?
I think I know.
Oh my god, it's not funny anymore. So there you have it, a rigorous definition of what a monogamous relationship is. It is a undirected, simple graph with precisely two vertices, or order 2, in degree 1. Okay, so you only have one edge, two vertices. Now, a poly relationship or polyamorous relationship is an undirected, simple graph. Well, we're going to assume first undirected. We can say this is a direct one when we do this, or when we put an arrowhead here at the end. That would be a directed, or that would be a give-take relationship, a GT relationship. So we put there a GT. Yeah, GT. That would now be a GT. 2P GT mono. And then the second type, this one here, is a 2P GG relationship. Mono. P1, P2 would be this. So give relationship is an undirected graph now. Would be that. Okay, so now let's talk about polyamorous relationships. A polyamorous relationship now is when we generalize this notion into n. So we're going to say now, instead of just 2 people, we have n amounts of people. So I'm going to raise the 2 now and say n. And instead of just being this, two-member set, we now have multiple set n. And then now we have a multi-edge or multi-member edge set R. So that would be something like this. Or, well, something else like that. Well, as long as you know that there are multiple vertices now, or wait, I'm going to put n here, and n. So now it's a poly. Instead of mono, it's now a poly. This poly, this is now poly. There. So this is this over here, actually this is not the same. This here, this give-take relationship would be a directed pseudo-graph. And then this give-give relationship is a undirected pseudo-graph. Again, we don't permit loops here, because when we talk about loops in the context of our theory, a loop on a person is a manifestation of, or an abstraction for narcissism. So the affection circles only back to the person in question here. Now it is already a given, it is already a universal sort of known fact that everyone loves themselves, okay? So everyone has an affection for themselves. So this would be an unnecessary thing to write. It's simply an abstraction for narcissism. So we're going to disregard this kind of graphs. But do notice that there are these kinds of relationships among people. That there are people that love other people only for the sake of those other people loving themselves. And they don't care about other people. Okay? So, yeah. But we want healthy types of relationships. So we are using non-loop permitting kinds of these things. Okay. Now you can say, well, the give-take relationship, wouldn't that be narcissistic? Because, well, the person just gives, right? He doesn't even get anything back in return. Well, the thing is, the partner or the partners could consent to, to them not giving anything, but only receiving, right? And it would still be somewhat beneficial to them both, and there's no narcissism here, so long as there's no loops. So, this is a poly relationship, and what I said was a mono relationship in the case of these things. So now, there will be multiple of these things. But if you have a graph if you have a poly relationship that's only directed, so I have this, and then this guy likes this other guy, and then this one likes this other person, and this one likes this other person. And usually these guys don't circle back. This is an affair. This is called an affair. So 1, 2, 3, 4, 5. 5p affair. 5p affair. And then this is our set M. If it's all undirected and these guys don't circle back to any other person, being receiving affection, this is an affair. So specifically, this is a directed, non-closed pseudograph. That would be an affair. And so now, okay, given all this, let's now prove that some of these guys are actually manifolds. Okay, so let's say I have a 5p GG relationship. 5G GG relationship. Or 4G. 4G GG. So it's a directed graph there. Now I'm going to show that this is homeomorphic to a subset of R. So what we're going to do now is have this set of these vertices, right? Or these vertices and the points. So we're all going to just collect it into one, G, and equip it with a metric. The Euclidean metric to be precise, which gives us a notion of length. Once you do that, we can show that it has a direct homeomorphism, or there's a morphism alpha that maps this onto REL, which n is a subset of. And since n is a subset of this, and it is a subset of R, we are essentially mapping, or we have a homeomorphism from this structure onto R. Well, okay. So I'm just gonna make it quick here. EM, I'm gonna explicitly define EM, or Euclidean metric, as, well, taking in two inputs G, or G1 and G2, both of these guys inside G, or a graph, and then spits out a real number, which is the length of their vertex. And that will be important in the next lecture, because that will tell us sort of the degree of the affection each member receives. So I guess I'll see you guys then in the next lecture.